Look at this lightning strike. A massive discharge of electricity superheats the air to 50,000 degrees. But as it hits the ground, the surrounding atmosphere remains completely static. There are no pressure ripples radiating outward, and no thunder. We operate under the assumption that when physical objects collide or energy is violently released, sound is the inevitable result. But just imagine a planetary anomaly where Earth's atmosphere instantly loses the ability to transmit mechanical pressure waves. While the human ear remains functional, the physics of the air itself have broken. Sound does not exist as an innate property of empty space. It is a strict mechanical dependency, governed by the precise elasticity and density of the molecules suspended in our atmosphere. When those atmospheric properties collapse, we enter a physical state called acoustic medium failure. To understand exactly how an atmosphere breaks acoustically, we have to model the specific thresholds of failure and track how the conservation of energy resolves silent, violent kinetic events. If the air loses its capacity to transmit pressure, the invisible mechanical fabric that connects physical actions to our sensory reality is instantly severed. To identify the breaking point, we first look at the baseline mechanics of Earth's air at the microscopic level, specifically the dense field of nitrogen and oxygen molecules. This animated diagram models how sound operates as mechanical energy traveling through a medium. On the left, a flat vertical surface pushes rapidly into the particle field. As the surface moves, it generates a longitudinal wave of pressure. You can see this as a visible band of high compression that immediately begins traveling outward. Zooming in on the particle level reveals a domino effect of kinetic transfer. Particle A is forced forward, colliding with particle B, transferring its kinetic momentum, and then retreating to its original baseline position. This sequential chain of compression travels away from the source until it impacts a receiver, like a flexible membrane or an eardrum, forcing it to vibrate. This entire mechanism relies on a narrow set of physical parameters regarding the precise density and elasticity of the gas mixture. Normal sound transmission is contingent on maintaining an unbroken, fluid chain of kinetic momentum transfer between adjacent particles. What specific physical thresholds must be crossed to halt this collision chain permanently? This split-screen visualization outlines the two boundaries of acoustic medium failure. On the left side, we model extreme atmospheric dispersion. The surface vibrates, but the particle field is incredibly sparse. Physicists define the average distance a molecule travels before colliding with another as the mean free path. If the atmosphere becomes too dispersed and the mean free path becomes too large, the kinetic momentum simply dissipates before a successful collision can happen. On the right side of the visualization, we see the opposing boundary condition, absolute atmospheric rigidity. Here, the particles are locked into a perfectly tight, unyielding lattice grid. This represents a theoretical state where molecular elasticity drops to zero, rendering the air infinitely rigid. When the vibrating surface strikes the grid, the particles refuse to compress or shift. The kinetic energy hits a complete dead end. Physics dictates a strict mechanical rule. Without localized compression, vibration transfer is impossible. Crossing either of these thresholds, an infinite mean free path that mimics a vacuum, or zero elasticity that creates a rigid grid, effectively mutes a planet by breaking the mechanics of momentum transfer. This shift raises a specific question of energy conservation. If a violent mechanical event, like a gunshot or a jet engine turbine, occurs in a non-acoustic atmosphere, where does that energy go? The law of conservation of energy applies regardless of the state of the atmosphere. Kinetic force cannot vanish just because a medium breaks. Under baseline conditions, a significant portion of explosive kinetic energy escapes the immediate area by radiating outward as an acoustic wave. But in a broken medium, that energy is forced into a thermodynamic pivot. This diagram charts a localized kinetic expansion, representing a gunshot blast, firing directly into a rigid particle grid. Because the expansion fails to propagate a pressure wave, the untransferred kinetic force is instantly absorbed into the air as heat, creating a stark thermal bloom. If continuous mechanical action takes place, like heavy machinery operating, heat builds exponentially at the point of contact, severely overheating the local environment rather than producing noise. The world is reduced to a pantomime of kinetic violence, stripped of its auditory weight. In a non-acoustic atmosphere, violent mechanical energy is trapped locally and resolved exclusively through rapid thermal dissipation. Scaling this microphysics model up to human infrastructure exposes immediate catastrophic vulnerabilities. Modern engineering relies on acoustic feedback loops to dictate structural safety and maintain situational awareness. This schematic visualizes a large industrial factory. We push in on a cross-section of a structural I-beam under immense load to isolate the mechanics of material stress. Normally, a microfracture tearing through steel emits warning acoustic frequencies before total failure. But in a mute atmosphere, the fracture expands to total collapse, with zero mechanical pressure waves emitted to warn bystanders. Secondary industrial hazards become equally invisible. High-pressure gas leaks expanding into the environment rely on fluid dynamics of pressure equalization that can no longer generate a sound. Even combustion loses its warning signs. A fire would consume materials rapidly, lacking the acoustic crackle of expanding gases. Without acoustic pressure waves to act as an early warning system, our entire industrial infrastructure becomes unnavigable and inherently lethal. Surviving this altered physics model would demand a severe shift in biological sensory processing. The human eardrum evolved exclusively to process airborne longitudinal waves. In this environment, the organ is completely useless. The required biological pivot means processing kinetic events through tactile sensory input via solid mediums. Humans would have to learn to detect low-frequency vibrations traveling through the ground, utilizing the fact that solid Earth maintains different elasticity variables than the broken atmosphere above it. The day the Earth goes silent marks a total mechanical failure of fluid dynamics. For life to comprehend the reality unfolding around it, it is forced to physically connect with the ground.